Let's start then. Common emitter amplifier. As usual, I just pose a few questions, interesting questions, which are pertinent to this particular topic here. One of them is, why can't I design one single amplifier that works for all applications? If you go to any company, say National Semiconductor or Texas Instrument, which make amplifiers, you'll find that they have hundreds of amplifiers listed. And the issue is, why can't I design one amplifier and sell it to all the people? You know, whoever wants it, just one amplifier satisfies the requirements of all of them. Why is it that I can't do it? Okay. The other one, which you are all familiar, maybe worried about, why does the output of an audio amplifier not sound so pleasing at higher volume? Apart from psychological reasons, if it's very loud, that's a different thing. But the quality of the sound goes down at very high volumes. The other one, how can one amplify a small DC signal? Okay, our initial discussion would all be related to time varying signals. Okay, I won't call it sinusoidal, I'll say time varying signals here. And, amplifying DC signals is a little bit of a problem. It's not straightforward, and you'll see why. Okay, so the amplifier that we have discussed so far, we have not called it a common emitter amplifier. We have seen that if you have a bipolar transistor, we would like to bias it in a manner shown here, R1, R2, RC, and RE. We'll put capacitors here, and we'll take the output here. This particular amplifier, you'll see in a minute, we call it common emitter amplifier. Okay. Yeah. The reason being is, you're applying input at the base side here, and the input is between base and emitter part, and the output you're taking at the collector, so the output is between collector and emitter part here. And therefore, emitter is a common terminal, which you can see more clearly when you draw the small signal model here. So in a small signal representation, as all of you know, what will happen is VCC will get shorted here to ground. And if I ignore the effects of capacitors here, capacitor will act as a short in the frequency range of interest here. So this point is ground. This capacitor will act as a short. And therefore, an R1 and R2 will come in parallel, which we are calling it as RB. And therefore, my amplifier looks like this here, where the transistor has been replaced by a simplified hybrid pi model here with an R pi. So we have omitted all the capacitors that are there in the transistor because we are talking about a frequency at which they don't affect my amplifier. Okay, yeah, I'll talk about that in more detail a little later on. Okay, so this is then the equivalent circuit that I get, small signal equivalent circuit for my amplifier here. And you can see clearly here that my signal is being applied. Vs that you see here is between base and emitter. And output that you're taking is also between collector and emitter here. Emitter becomes a small signal ground. And emitter, therefore, is common to both input as well as output side of the circuit here. If I look upon it as a two-port small signal circuit, so the input port is between base and emitter. The output port is between collector and emitter here. So emitter is the common terminal, and we call this amplifier as a common emitter amplifier. All right, this is what we have already done about the common emitter amplifier when it comes to biasing. We have seen that these are all the relevant equations here. We know that we have to calculate, last lecture we saw we have to calculate the voltage here at this particular point, VBB here. RB is R1 parallel R2. This is how we find IC here. This talks about the sensitivity of the current to beta here, and we know that the design criteria, things that we have to keep in mind while designing the biasing circuit is RE should be much larger than RB by beta here in order to ensure that sensitivity is small, and we would like to keep VBB minus VBE much larger than the change in VBE due to temperature in order to make the biasing temperature insensitive. So these are the things that we've already seen, and these equations and these constraints will help us to design the biasing circuit. Once we decide the collector current that I want or the collector emitter voltage that I want, based on that, we'll use these equations and these constraints to arrive at values of R1, R2, RE, and all that. Okay. So that, and of course, after doing all these analysis, remember they're all based on the fact that the transistor is in forward active. So make sure that you check VCE is larger than VCE sat here. If you're doing analysis, you have to check that this is true here. All right, so small signal, so if I want to go forward with my amplifier, I have to do the analysis of the small signal analysis of the circuit here. So again, I've shown it, but now I've shown it in a little bit more detail. So R1 and R2 as usual, remember this is ground, so R1 and R2 are in parallel, so remember RB is that. Now I've not neglected any capacitors. I've put CB here, we have put CE, RE here, and we put CC here. We put all the capacitances there. Not only that, the transistor has been replaced by its general model, where I have RPi, GMVB, and R0. In addition to that, I've put here CPi, I've put here CMu, and I've even put these substrate capacitance that you see here. So all the capacitors have been put. In addition, I've also put a base resistance here, RBB, base spreading resistance. So this is a more general circuit for this particular amplifier. Okay. Now all other circuits that we do for our that we use for our analysis are all derived from here by making some assumption. Okay. And the first thing that we do is the following. If I look at this particular circuit and I'm interested, let's say, in V0 divided by Vs, which is the gain, and obviously because of the capacitors, my gain is going to be a function of frequency because of the presence of capacitors here. In general, this is what I obtain. This is a graph that I've shown earlier. We obtain a graph like this if I plot the magnitude of the gain. This is the magnitude of the gain against frequency. What I would see is, for the amplifier that I showed you, we'll see a behavior like this here. Okay? And it's understandable why we call each one of these regions by the names here. This is a low frequency region here. Gain is falling with frequency here. This is a high frequency region here. Gain is falling again with frequency here. And this is a region which is independent of frequency. We call it mid-frequency region here. And this is a region, as I explained earlier, is of interest to us because signals of different frequencies undergo the same gain value here. And therefore, the signal doesn't get distorted. Okay. And so this is the range of frequency that I'm interested in. Now, obviously, if you find that there is a range of frequency where my gain is independent of frequency, it means what? My capacitors are not active. They're not influencing my circuit. Here, of course, capacitors must be active. Capacitors must be influencing my circuit. Here also, capacitors must be active. But this is the region where none of the capacitors play a significant role. Okay. So let's look at this in a little bit more here. Now, when I look at this particular circuit, let's keep certain numbers in mind which will help us to understand these three regions here. Okay. Some numbers are the external capacitors. You'll see later on why we put, we know why we want to bypass this particular capacitor here. These external capacitors are typically, in microfarads range. 10 microfarad, 50 microfarad, maybe even 100 microfarad, depending on the situation here. Okay. So all these external capacitors that you see here are typically in microfarads range. CE here, CC here, CB here, all these external capacitors. They are in microfarads range here. The internal transistor capacitances, if you go back to our earlier lecture, we had given you some typical values. These are in picofarads range. Okay. Again, they will vary. If you have a transistor which is very small, this can become sub-picofarad. If you have a large transistor, it could become 10 picofarad, 100 picofarad. But a number to keep in mind is in picofarad scale. Okay. The idea is look at the difference here. This is picofarad. This is microfarad here. 6 orders of magnitude difference between these two. The other thing is RPi, RE may be typically, let's say, 1K. Okay. Again, these things will vary. If I bias my transistor at 1 milliampere current, RPi is 2.6 kilo for a beta of 100. If I bias it at very low currents, obviously RPi will go up. Okay. Again, so these things all vary, but as a number to keep in mind, let's say is a 1K here, maybe 2K here or whatever. Right. So these are the numbers. So now, if I look at this particular capacitor, what is it? Internal transistor capacitance. If I look at 1 picofarad and I calculate its impedance 1 by omega C, what I find is that its impedance is 159 mega ohm at 1 kilohertz and 15.9 kilo ohm at 10 megahertz here. So what you are seeing here is that if I look at lower frequencies, 1 kilohertz, 10 hertz, 100 hertz, 10 kilohertz, the impedance due to CMu, CPi is very large. Large as compared to what? Let's say RPi. RPi is what? 1 kilo ohm. So it's a very large value here. 159 mega ohms here. Very large value. And therefore, for these smaller frequencies, I can consider my capacitors as open circuit, because they are much larger than my the other impedances that are there in the circuit here. Okay, so I'll consider them at lower frequencies as open here. C mu, C pi, all of them are open. Okay, while if I go to higher frequencies, I see that 10 megahertz, I see the impedance becomes 15.9 kilo ohm, and then of course is starting to becoming comparable. I can't neglect it. Okay, so for lower, you are seeing that there's a whole range of frequencies for which the internal transistor capacitances have impedance which is very large, and I can neglect them. But a stage comes, of course, at higher frequencies where they become significant. So that's the picture about internal transistor capacitances. They become important at higher frequencies. At which frequency will they become important? Obviously, I have to, I need a value of the capacitor, and I have to look at the impedance here and compare it with the rest of the impedances in my circuit, and then decide at what point do they become significant. Okay. Look at now the external capacitors. 10 microfarad here, CB and CC here. 10 microfarad capacitor around 1 kilohertz poses a value of 15.9 ohms. And 10 hertz, it poses 1.59 kilo ohm. So what can I say? These capacitors, CE and CB and CC, will become important to us at low frequencies, because now they are becoming comparable with my resistances and all that are there. So they will become important at lower frequencies, and at higher frequencies, even at 1 kilohertz, it's only 15.9 ohms. If I go to 10 kilo ohm, it's only 1.5 ohms. So what you're saying is that all these external capacitors that I put in, they will all become insignificant as I go to higher frequencies. Insignificant means shorts, because their impedance is very small. So at higher frequencies, I can consider all of them as CB and CE and CC all as shorts. If I go to sufficiently lower frequency, then of course they're significant, their impedance matters, and we have to take them into account. Okay, so what you're seeing is that I have a lot of capacitors in my circuit, but they can be divided into two classes. One is the internal capacitances, which become important only at higher frequencies, and the external capacitances, which become important only at lower frequencies. And importance means something else. Lower frequencies, I can consider them as open, and higher frequencies, I can consider these as shorts. Okay, so this is the simplification that I can do now. This is my original circuit. If I go to lower frequency, then what I need to do is keep my external capacitances here. CE, CB, and CC I need to keep here. Transistor capacitances, the impedance is very large, and I can neglect it here. So that's the circuit that we have to solve for lower frequencies. Okay, for upper frequencies, the external capacitances are all shorts, and the internal capacitances is what I need to consider here. Okay, so that's for higher frequency here. In between, I can consider transistor capacitances as open, external capacitance as short, and this is the region here where we don't get any capacitors, and that's the mid-frequency range here. Okay, so these are the three ranges in which you can divide the operation of your transistor, and you can see which capacitors are playing role in which regions. Okay, most of the time we spend here because that's of our interest, mid-frequency here. Here, our interest is only in knowing when does the low-frequency region begin. And here again, our interest is in knowing when does the high-frequency region begin. While here, we are interested in all the properties of the amplifier. Okay, so this is the main operating region here, and this is our primary interest. Okay, so that's where we'll spend most of the time, and then later on we'll find out at what frequency do I need to consider this, at what frequency do I need to consider this. Okay, so back again then to this circuit here, to this circuit mid-frequency, and now what I've done is at various points I'll make some simplifications here. So RBB is there in mid-frequency range. In general, I'll neglect RBB. Okay, if you want to do more accurate analysis, you can include RBB. Is sort of trivial, but just for simplicity, I'll ignore RBB here. Okay, so that's the circuit that we get here, our small signal circuit, and now it's straightforward to analyze here. We see Vs is basically equal to base emitter voltage here, small signal base emitter voltage here, and then that's the current here. This current flows through a parallel combination of all of them, and therefore we get gain V0 by Vs, which is equal to minus Gm R0 parallel Rc parallel RL here. And it's easy to show here that R0 in general is much larger than Rc. If you recall, R0 is equal to Va by ICQ, and if I take the ratio of R0 by Rc, we get Va by ICQ times Rc here, and Va, as I said, maybe 50 or 100 volts of that order, ICQ Rc maybe 2 volts, 3 volts, and therefore it shows that this quantity is much larger than 1 in general, okay, and therefore R0 is in general much larger than Rc, and one can make that approximation in this case, that R0, one can ignore it, and we get GMRC parallel RL here. Open circuit gain, if I didn't have RL here, RL goes to infinity, that's my open circuit gain, that's equal to GMRC, and GM if I put in the value here, ICQ by VT here, so we get ICRC by VT. Okay, so the amplifier gain as a open circuit gain depends on ICRC drop here, and the gain of course depends on VT, so it's highly temperature dependent, the gain. VT is directly proportional to temperature. Higher temperature means lower gain here. Okay. Now, this is the point that I have told earlier, and it's good to keep in mind that note how the output voltage is being developed. Look, the steps that are there. The Vs, the input that you apply here, it changes VBE. Changes VBE. That's the first step. You want the input to change the base emitter voltage here. The base emitter voltage translates into a change in collector current here, GMVBE here, GMVB here. And then GMVBE flows through this parallel combination here and develops the output. So you can see a sort of three-step process. V0 affecting VBE, Vs affecting VBE, that's the first step. The second step is this translation between here and here, the current, and the current then flowing across a resistor and developing the voltage. Okay, so you would like each one of these steps to be efficient, that you want the entire input voltage that you apply to appear across base emitter. If it gets dropped somewhere else, then the gain will get affected. That first step becomes inefficient, there's a loss here, and the gain will get affected. And remember, I said there was an RBB here. There was an RBB here which I'm neglecting. So what would happen is actually the Vs that is there, some part of it will get dropped across RBB, and only a fraction will appear across R pi. Okay, and now what happens is RBB, the base resistance here, is to a first order approximation constant, doesn't depend on bias that much, while this one depends on your bias. You know, if I apply a large collector current, then this R pi becomes smaller. If I apply a smaller current, R pi is inversely proportional to collector current. This becomes larger here. So depending on how you bias, where you bias, you may find the entire Vs goes over here, or you may find there is a significant loss here. Okay. So for example, if you actually go and measure a transistor, if you use a simplified model, it will predict a gain. But when you actually go and measure, because you have neglected RBB, you may get a smaller gain than what you predict from here. So keep in mind there is an RBB here which we are neglecting. Okay. And so this tells us the things that we are looking for in amplification here. These are the three steps here. V0, Vs to VBE, VBE to GMVBE here, and GMVBE to RC parallel R. Okay. And then you develop these now. Alright, so besides gain, there are other things which are important. In our discussion on amplifiers, we saw input resistance is important. So input resistance of an amplifier means looking from here. This is our amplifier, common emitter amplifier, and the resistance looking from here. And we've already gone through this part here. So what the consequence of input resistance is, the voltage that you apply, you know, if you have a source resistance, only a part of the voltage goes to the amplifier here. Some voltage gets dropped here. And we have seen these here. Vin is on, the voltage that appears across the amplifier is here. V0 is given here. And therefore, what we find is we would like input resistance to be as large as possible, because that ensures that whatever is my signal, Vs, it goes to my amplifier. I want it to go to the input of the amplifier. I don't want my signal to be dropped across Rs. And the way to ensure this is that the resistance seen into the amplifier, when you look into the amplifier, that's much larger than Rs. Okay? So, when I say input resistance has to be high, well, you know, the question that you should ask is how high? And that depends on how much is my Rs. Okay? If my Rs is 10 ohm, 1 kilo ohm is very high. But if my Rs itself is 1 kilo ohm, then I'm looking for 10 kilo ohms or 100 kilo ohms. So how high and all that depends on the value of RS that is there here. Okay, but in general, high input resistance is what we desire. How do you determine input resistance? Well, what you do is, as I said, input resistance is resistance looking from the input port here. So what you do is, in an amplifier, when you analyze, just put a source here, Vx, and there's a current Ix, and input resistance is simply Vx by Ix. That's what, in analysis, that's what you do. Okay? To the amplifier here, Vx, Ix, and then do this ratio, and you get the resistance here. So let's do it for a common emitter amplifier. For a common emitter amplifier, my amplifier starts from here. Please understand where the amplifier is starting from this point here. The whole thing is my amplifier. Okay? And so I apply an input Vs. You can say Vs or Vx, whatever, it doesn't matter. And I look at this current, and my input resistance is going to be Vs divided by Is. Okay, so this is the beginning of my amplifier here at this point. And therefore, I can see very clearly that the input resistance Vs by Is is nothing but Rb in parallel with R pi. Okay, Rb parallel R pi. And in general, R pi is the smaller quantity here, R pi is the larger quantity here. And if you want input resistance to be as high as possible, then one of the things that you may want to do is, you may want to make Rb much larger than R pi. Okay, then input resistance is simply equal to R pi here. Okay, so this is one of the things that we try to do is that keep Rb, design it in such a way that Rb is much larger than R pi. Therefore, the Rb coming in parallel with R pi doesn't reduce my resistance. My resistance gets defined by R pi here. Okay. Output is similar, is the resistance looking from the output side here. And we have seen this picture that from the output side, you can represent your amplifier as open circuit gain AV0 times Vin in series with R0. And we have done all of this. And we have seen that what you want is output resistance to be as low as possible here. So whatever voltage is generated here, you want this voltage to go to the load, and you don't want it to get dropped across R0, and therefore you're looking for R0 as small as possible here. Again, all that you're looking for is R0 significantly smaller than R. That's all. Okay. How do I determine output resistance? Well, if I want to resistance from looking from here, what I do is I put a source here, Vx, Ix here, and I ground the input. I remove the input here. And R0 is simply Vx divided by Ix. So given any circuit, amplifier circuit, if you want to determine output resistance, remove the source, put it to ground, attach a voltage here, do the ratio Vx by Ix, it will give you R0. Okay. So let's do that for here. This was our amplifier. We'll remove the source. Okay. So we'll get this circuit. We remove the source, meaning we short it. Voltage sources are shorted. If it were a current source, I would open circuit it. Okay. That's what removing means. And here at this point, we attach a Vx, Ix here. And note, there is no load resistance. When I define output resistance, load resistance is not included in the definition here. Okay. So Vx by Ix, and now it is straightforward. If this is a short, I know that V pi is 0. There's no source of current in this loop here. So this current source is also open circuit. And my Vx by Ix, then there's open circuit here, 0 current. And the circuit simplifies to RC parallel R0 here. And so my output resistance is RC parallel R0. And R0 we said is a very large, in general much larger than RC. So we can approximate R0 by simply RC. Okay. So it's very simple. Output resistance for this amplifier is simply RC here, because R0 is larger. Okay. There are other quantities. If I'm making a voltage amplifier, I may not be directly interested in the current gain of the amplifier, but let's calculate it nevertheless. So we define short circuit gain as, of short circuit current gain of the amplifier is you take an output and you short it to ground, and you look at the short circuit current, output current divided by input current here. Okay. And therefore it's called current gain under short circuit condition. Now we've already seen that given an amplifier, it need not be common emitter amplifier. It could be any amplifier. We said that it can be written like this here. V in, AV0 times V in and R0. Now this one, I can also write it as this is like a Thevenin's equivalent. I can write it as a Norton's equivalent. So a voltage source in series with a resistor can be written as a current source in parallel with the resistor here. I could do that. And now, so these are straightforward things. So I'm going relatively quickly here. So now if I want to short it, I'll short the output here. And so the current that flows into my output port here, I0 is simply equal to AV0 times V in by R0. Okay. And input current is V in divided by R in. Alright. So we converted it into Norton's equivalent, and now I'm looking at short circuit current gain. So I short the output here, I look at the current, and this current is nothing but the Norton's current here. And the input current from this side is whatever is the voltage here divided by Rn. So now I take the ratio, I0 is here, In is here, I take the ratio here, and the short circuit current gain is simply equal to AV0 Rn by R0. So what it is saying is, if you've already done the calculation for your open circuit gain, input resistance, output resistance, the short circuit current gain is not an independent parameter. It can be derived from the ones that you've already calculated. Okay. Now, just as somebody may ask, may be interested in not just short circuit current gain, but current gain with the load resistor, not with the short circuit current. So this also, again, these are straightforward. Again, all that I do is, this is the model that I have. I put an RL here. I can again calculate what is I0. All that I have is this current will divide between these two. So I can calculate I0. Again, I know In, and therefore I can calculate, the current gain here. So these are straightforward. Once you write down the circuit, it's straightforward. Okay. All right. So that's the summary of what we have done so far. Small signal analysis. We have said that the gain of the amplifier is GM R0 parallel RC parallel RL. We have said that we'll make an approximation that R0 can be neglected. So it's GM RC then parallel RL, and open circuit gain. So what you see here is AV will always be less than or equal to open circuit gain, which is equal to GM RC. Okay. So forget R0 for a moment. Gain then is simply GM RC parallel RL. Open circuit gain is GM RC, and therefore my gain will always be less than or equal to the open circuit gain, which is GM RC, which is equal to ICQ RC by VT. So what it is telling you is that if you make this amplifier, the upper limit on gain is ICQ RC by VT. That's the upper limit on gain, when load resistance is very high. If load resistance is smaller, then it will come in parallel, it will pull the gain further down. Rin, we said, is RB parallel RPi, and we said most of the time what we'll do is make RB, try to make RB larger than RPi, considerably larger than RPi, and therefore my input resistance will always be less than or equal to RPi from here. And RPi is VT by ICQ into beta. So my input resistance, the limit on input resistance is this quantity here. Okay. And R0 is approximately equal to RC. Now we've just learned the following. For a voltage amplifier, we would like high voltage gain, high input resistance, and we would like low output resistance. And I'm sure you can see the conflict. If I want my input resistance to be high, and suppose I'm given a transistor of a certain beta, what can I do? If I want my input resistance to be high, I will try to bias my transistor at a low collector current. And if I try to bias it at low collector current, what will happen to my gain? My gain will go down. My gain will go down because if I try to make ICQ small, then ICQ small will result in smaller gain. Now you may say, well, then if you make ICQ small, why don't you increase RC to compensate for that? So fine. What you're saying is, I can make my Rin large, I can keep my voltage gain constant, but then what will happen to output resistance? That becomes large. So I'm sure now you are seeing a trade-off. If you try to make AV large, how can you make AV large? Either you will increase RC. If you increase RC, what happens to your output resistance? It becomes bad. It becomes high. If you don't want to touch RC, if you want to increase gain by increasing ICQ, well, then your input resistance goes down. Okay. So you're finding that all these three are related together. And it's very simple to find out what the relationship is. So I have AV is less than this value. Rin is less than this value. R0 is approximately equal to RC. So suppose I multiply these two together, AV into Rin. So I get ICQ RC by VT into VT ICQ by beta. So this turns out to be beta times RC. And then it's easy to take these two, and I can get AV into Rin divided by R0 is less than or equal to beta. So right hand side is a constant, which is beta or less than that, some quantity. And left hand side is, is telling you what your gain, input and output resistance can be. So remember what I said, you want high voltage gain. If you try to increase the voltage gain, this equation is telling you two things you'll have to do. Either you compromise Rin, make Rin small, or you make R0 large. That's the only possibility that you have. Okay. So it's telling you that these three are all related together and there's a trade-off. There's a trade-off between these quantities here. And now that tells you, it sort of in a simplified way answers, why is it that I can't design one amplifier which suits everybody? Why I can't do that? Because one person may require a input resistance of 100K. And so you will accordingly, if it's 100K, you will accordingly design it for that one. All right. So, and another one may require output resistance of 10 ohms or whatever. So you'll design it accordingly. One single amplifier which gives you 100K, 10 ohms, 100 gain of that is not possible. It's simply not possible, as you can see here. So an improved quantity here comes at the expense of the others. So depending on which one is more important or less important, one will design it accordingly. Okay, so this tells you the trade-offs between gain, input resistance, and output resistance. And although we are talking about common emitter, this is, in general, you'll find this is true about voltage amplifiers. You'll see this trade-off between gain, input resistance, and output resistance. Okay. So suppose I ask this question. Say, you are a designer of a common emitter amplifier. You have a company. Somebody comes and says, give me an amplifier with a gain of 100, 2K, and 1K. What will you do? He says, design an amplifier for me with these specs. Is it possible? Not possible. Huh? Well, you'll do this, right? You'll say AV. You know now what are the trade-offs. So you'll do AV into Rn by R0 and have a beta of 100. And so you say, well, it's not possible, right? So what will you say? It's not possible, but then he'll say, what can you do for me? Yeah, right? So now you can play around with this. You can say, well, I can give you a gain of 100. Maybe I can give you a Rn of 1K and R0 1K. That may be possible, right? And if he's not happy, so you can go back and forth. Now, back and forth, and you can arrive at what kind of specs can you give. But suppose you didn't have this equation. You didn't know about the trade-offs. He comes to you and says, give me this one. And so you sit down, you work out all the numbers, R1, R2, RC, RE, and after a few hours you say, well, it's not possible. Then he says, what can you give? If you didn't know this, then how would you answer that? He says, okay, you can't give me 100, Rn, 2K, and 1K. Give me something which is close to that. Then how do you tell that? So what is very important is that as a designer, you have to understand the trade-offs. What is it, if you can't give this, well, you realize now I could reduce Rn and I could increase AV and, things like that. Okay. So this equation is very simplified and, not simplified. I would say this is reasonably correct and gives you what happens in a common emitter amplifier stage like this. Okay. Tells you the trade-offs that are there. All right, so this is similar. Let's say you have an amplifier which has a gain of 85, 1K and 1K here. How do I double the voltage gain? First of all, how will you double? You're asked to double the voltage gain. What will you do? Well, two things you have. Remember, keep at the back of your mind, gain is IC RC by VT. So two things you have. Either you will try and change this RC or you will try and increase IC. Okay. Now suppose you don't want to touch this R0, so you will not change RC. Then you have to change IC. How will you change IC? How will you change IC? Which resistor would you touch? R2. Why R2? So I want to increase RC. I want to increase current. Who decides the current? Well, go back and look at the, current is, don't forget this equation. What decides the current? Well, I have to go back a lot. Here, this decides the current. Keep this in mind. VBB minus VBE. VBE you can't do much. It's close to 0.7, 0.6 or whatever it is. You can't do much. This quantity, we want to make it small. So what you are left with is VBB by RE. These are the two things. So how do you change VBB? You change by altering the ratio here. R1, R2 ratio here. That's what changes VBB here. And the other thing is RE. So either you keep the ratios R1, R2 the same, and then you alter RE. And therefore, you can increase or decrease the current by simply changing RE here. Or if you don't want to touch RE, then this is what you control here, RBB, R1, R2. Okay. All right. So again, let me scroll back to where we were. Okay. Current gain. All right. So this is where we are. So these are the trade-offs that are there here. Okay, let's take an example. So I have a amplifier here, 10K, RCs 4K, 5.3K here, and the circuit is given. So the first thing that I'll do with this amplifier is I will do although I'm interested in voltage gain, input resistance, output resistance, I cannot calculate any of those quantities unless I know the bias point. So it starts with bias point, and bias point analysis starts by calculating RB. Is R1 parallel R2? And then we have equations for IC, so we calculate 1 milliampere here. We calculate VCEQ. I'm now skipping the steps, 2.75 volt here. So my transistor is biased in active region here. VE, the voltage here is 5.3. All right, so this is my DC. Once I know my bias point, then I calculate all the small signal parameters here, GM, R pi, R naught. And R naught is 100K, RC is 4K here, 25 times larger. So, as an approximation, I can neglect this effect here. Voltage gain now, AV0 is what? GM, simply times RC, and that comes out to be 152. Rn is R pi in parallel with RB. Now what happens is, note R pi is 2.6 kilo ohm and RB is 5K. So therefore, RB is affecting my input resistance here. So it's not a good design in that sense. This should have been higher. And so this is affecting my input resistance here. It has fallen from 2.6 to 1.7K here. And R0, of course, is simply RC 4K here. If I multiply them together, AV0 Rn by R0, it tells you AV Rn by R0 is 64.6, which is obviously less than beta here. Now, the reason why it is not close to beta is because of this Rn. Rn, this circuit is not so well designed. RB is becoming comparable with R pi. If I had chosen RB as much larger than R pi, I would have gotten here 2.6, and then the ratio, this term would have gotten closer to beta of a particular value here. Note also that this equation can allow you to select a transistor. Suppose your goal was to design a amplifier with a certain gain, input and output resistances here. And in this case, let's say we get a gain of 152. If somebody asks you for, similar specs, but says design something with a gain of 300. Now, that person who's asking you to design is not telling you to choose a particular transistor. It's up to you to choose a transistor here. So now you can go into the data sheets and look for, is there a transistor, if I want to double this gain without altering Rn and R0, obviously I require a double beta. So you can go ahead and look at the data sheets. Is there any transistor which gives me a transistor with a beta of 300 here? So it would help you in selecting the transistor as well, this particular equation. And with that transistor with a beta of 300, you may be okay, and you can give a gain which is 300 here, Rn of so much and R0 of so much here. So this equation can also help you in selecting an appropriate transistor. So AV0 is 152. Now look, the moment I put a load, gain starts falling. 152 was open circuit gain. If I put a load of 1K, the gain falls to 30. It just falls to 30. If I put 100 ohms here, gain falls to 3.7. Why is the gain falling so much with RL? Because my output resistance is 4K. And when you connect RL, which is smaller than output resistance here, most of the voltage is getting dropped here, less is appearing here. Okay? And therefore the gain is falling rapidly. Alright? So if you wanted to use this amplifier with an RL of 100 ohms, then R0, RC should have been chosen much smaller than this here. And therefore, then you can appropriately redesign the amplifier. Alright, this is an interesting question. Is it possible to get a gain of 100 here? So the idea is, again, as I said, somebody comes to you and says, design an amplifier with a gain of 100. Okay? And it has to run on 1.5 volt battery. Okay? And this is the only amplifier you know. You don't know enough right now. So that's the only amplifier you know. And can you design it to run on 1.5 volt battery and give a gain of 100? Is that possible? And how would you do that? How would you quickly check whether this is possible or not? Well, we know that gain AV is less than or equal to ICQ RC by VT. Right? We know that. So ICQ RC by VT then has to be 100. VT is how much? 26 millivolt. 26 millivolt multiplied by 100. 2.6 volts. So I need an ICQ RC of the drop ICQ RC itself of 2.6 volt. How am I going to get it with 1.5 volt? Okay. All right. So you can very quickly say, well, this is not possible. I need voltages which are considerably larger. If you want a gain of 100, I need voltages which are considerably larger than 2.6 volt. Because I want a drop here, I will like a drop here, and I will like a drop here. And therefore, it's also illustrating that the difficulty in building up enough gain with low supply voltage here. 1.5 volt battery getting a gain of 100 is not possible, according to this amplifier here. On the other hand, if I give you a 12 volt battery, then obviously you can easily design it. Okay, so it's bringing out the supply voltage dependence here. All right, let me stop here and